Okay, so we are in our last lecture of this long lecture series, and we have two more problems to finish in this class. And let us start with the first problem. We have a Lagrangian given, which is given by half m1 x dot square plus m2 y dot square, and there is a coupling term in velocity. That is something very unique, we do not see that very often, and there is a potential term. And we have to find out the normal mode frequencies. So, there is not much to be done except some basic calculation. Okay. So, let us start with this Lagrangian L, which is given by half m1 x dot square plus m2 y dot square, right, plus beta x dot y dot minus alpha by 2 x square plus y square. Very good. Now, first let us separate out the kinetic energy part, which will be simply this and the potential energy, which will be V equal to alpha by 2 x square plus y square. So, it is a two mass system where there is a coupling in the velocity, there is a coupling factor in velocity, which is very unique. We generally do not see coupling factors in velocities, but think of a situation where two masses are connected by some spring arrangement, where the kinetic energy, in order to find out kinetic energy, you do not have to take individual displacements square, but as a whole you have to take x 1 plus x 1 dot plus x 2 dot whole square. If you do that, or x dot plus y dots whole square, there will be a cross term coming in. So, you can think of a situation, or I will leave it to you as an exercise on mental exercise on thinking which of the physical systems will give rise to this type of cross term. Anyway, so let us write A, which is in this case m1 by 2, m1 by 2, and just like we did for cross terms in potential energy, we have to take this as beta by 2 x dot y dot plus beta by 2 y dot x dot. So, if we do that, so we have to write this term as beta by 2 x dot y dot plus beta by 2 y dot x dot. So, if we do that, we get beta by 2 here and beta by 2 here. Okay. Similarly, we can solve, or we can write B, and here B is the potential energy is diagonal in nature, there is no cross term. So, it is alpha by 2, 0, 0. Very good. Now, we have to find out. So, I chose this problem primarily because this is something very unique, we do not see that often. Now, we have to solve in order to get the eigen frequencies, we just have to solve determinant B minus AP square equal to 0, right. B minus AP square equal to 0, and if we write it explicitly, it will be alpha by 2 minus m1 by 2 p square beta by 2 p square. Do not forget that AP square means whenever we have a non-zero term in A matrix, we have to write a p square, multiply that with a p square and write that. So, B by 2 p square term will come in the off diagonal terms also. Similarly, here also we have to write beta by 2 p square, and diagonal term will be alpha by 2 minus m2 p square by 2, which will be equal to 0. Okay. So, this is the equation we have to solve in order to get p's. So, in order to solve this, we have to open the bracket, and let us do that. It will be alpha by 2 minus m1 by 2 p square alpha by 2 minus m2 by 2 p square minus beta square by 4 p square equal to 0. So, this is the equation, and if we okay, what do we need to do now? Okay. So, this is an equation where things will not be so simple, but anyway it is a quadratic equation. That's a good thing about quadratic equation, that whenever we have a quadratic in some certain sense, we can always find a solution very easily. So, let us do one thing, let us open up the bracket for this term and m1 m2 by 4. So, between these two terms it will be p to the power 4, and okay, between this and this it will be minus m1 by m1 alpha by 4 p square. Between this and this it will be minus m2 alpha by 4 p square, and last term will be alpha square by 4 minus beta square by 4 p square equal to 0. Okay. The simplest thing to do is get rid of this force. Okay. All 4s are gone. Okay. And then bring all the coefficients of p square together. So, you can write it as m1 m2 p to the power 4 minus okay, minus m1 alpha, right, m1 alpha, or rather m1 plus m2 alpha minus beta square, right, p square plus alpha square, which will be equal to 0, right. And next is straightforward. So, we do not worry about this anymore. Rest is straightforward. We simply can write p square, because it is a quadratic equation. It will be there was a mistake. Okay, there was a mistake, right? Sorry, it will be, this is p to the power 4, right, because the last term was, right. So, it will be p to the power 4. Okay. So, there will be no beta square here, but it will be m1 m2 minus beta square, right. Okay. Okay. So, this is once again it is a quadratic equation. So, we have to write as minus b, which will be m1. So, we know that for ax square plus bx plus c equal to 0, we can write x is equal to minus b plus minus root over b square minus 4ac by 2a. This is a very familiar form, and let us try this out. m1 plus m2 times alpha plus minus root over m1 plus m2 times alpha square minus 4ac. B square minus 4ac. So, 4 alpha square into m1 m2 minus beta square by 2 m1 plus m2 alpha. Okay. So, that is the final form. Let me just see if it is correct. Okay, so first term is fine, second term is also fine, third term is also fine, and the denominator is also fine. Very good. So, it is a sorry, denominator has some problem. Just give me a second. M1 M2 minus sorry this will go to the denominator, M1 M2 minus beta square, sorry. Okay. So, it is something that is very ugly, as in we do not have any pattern in it, but if you take simpler assumptions, like if you get a situation where M1 is equal to M2, I can assure you that it will come to a much more simpler form. Anyway, that was not the objective. I mean, this is the algebra which everyone can do. My objective was to show you what happens if we have a cross term in velocity in the kinetic energy expression. So, how to write this matrices and how to solve for the equation, because most common mistake people would make in that situation is they would not consider p square for the non-diagonal terms. So, that is why I took this example. So, it is not important to it was not never very important to show you how this algebra works. This you can always figure out yourself. Anyway, so this is the form, and let us move to our last problem, which will take some time and some understanding. That is a bit complicated problem, and I will tell you something, you will not find this problem in any of the standard textbook, nowhere you will find it. So, I had to really dig deep in order to get the get a formal solution of this problem. The problem is, once again we are considering triatomic molecule, but this time we are considering bending. See, I think I told you already in the class, beginning of the class, that beginning of this discussion of small oscillation, that triatomic molecules have stretching modes as well as bending modes, right. Now, what happens in stretching is covered everywhere. If you look for bending mode of, for example, carbon dioxide, which is a very very well studied triatomic molecule, you will not gain much insight. I mean, at least in the textbook levels, I have never found anything that deals with the bending. There are certain, of course, there are lots of research on it, because the bending modes and bending vibration frequencies of carbon dioxide is well reported, studied in spectroscopy, used in carbon dioxide laser, everything, but there is no formal description on how to get to these bending modes. Anyway, I found it from somewhere that it is reasonable to consider the bending angle to be the free parameter. So, typically what happens in a bending, let us say we have a triatomic molecule, when it bends, okay, it can also change the bond length, because there are certain certain chemical interactions which are also slightly orientation dependent. So, if the bending is changing, that means the relative orientation, see, each bonding is a electronic bond, covalent bond. So, there are two electron clouds overlapping. Moment you bend it, moment a bond is bended, the local configuration of these electron clouds are changing slightly. So, the bond length in practice will change, although very little, but it will change. But I have found somewhere that finally that actually for bending we can take we can think of it as if the major contribution of kinetic energy and potential energy when it is bending, or potential energy, is coming not from the bond length change, but from the angle. So, it is an angle dependent phenomena. So, which is very contradictory in terms of the compared to the stretching modes, where the angle angle does not change, but the bond length changes, and the potential energy is a function of the change of bond length only. Okay. So, let us go into the problem. Okay. So, consider bending motion of linear triatomic molecule, consider the potential energy to be a function of bending angle only, which is given by V. So, V is approximately half k square x theta square, where A is the equilibrium bond length and not of bond stretching. assuming triatomic molecule executing bending oscillation in z direction, there is a note that actually z and y directions are degenerate, I equivalent in terms of energy. So, we have to express kinetic energy and potential energy matrices in terms of Z1, Z2 and Z3 and solve for normal frequencies and amplitude, then comment on the nature of motion. Okay. So, the first part, see the second and third part is something that we or part B of this problem is something that we have already done many times for many different types of kinetic energy and potential energy matrices. But part A is something that probably we have not handled this type of situation. Okay, so let us start with this. How do you define the bending angle? That is a main question. Okay, so this is the equilibrium configuration, let us say, without any bending. So, we are not talking about stretching here, it is only bending. So, there is no bending angle and the relative angle between these three atoms are 0. Now, let us say we have a situation where we have a bending of the molecule. So, let us say this is molecule atom 1, atom 2 and atom 3 and we have masses small m, capital M, small m. Now, let us assume that this one has bended with a angle theta 1 and this one has bended with an angle theta 2. Now, what is the total bending angle? How do you define it? What we can do is, we can consider it as if only, okay. So, you see relative angle between this and this still remains 0, there is no relative angle. Now, what we can do is, we can consider this situation as if these two are remaining fixed and the third one has bended to this position with an angle theta 1 plus theta 2. So, it again it is essentially it is a 2 coordinate or rather 2, yeah. So, it is just an alternative representation. We can either think of it that this one has bended by an angle theta 1 and this one has bended by an angle theta 2, but or what we can do is, we can think that this one is stationary and the total bending angle we can convert it to theta 1 plus theta 2, we can translate it to theta 1 plus theta 2. So, we will do that, and if we do that, the potential energy V will be half A S square theta 1 plus theta 2 whole square. Now, also we have to make a assumption, very clever assumption here. Without that, we will not be able to translate this into the standard coordinates we are dealing with. So, when a bending motion takes place, what happens is, molecules are moving up or down along the z direction. Let us assume this is z, it could be y as well, as I said in the problem note, that z and y directions, how will you distinguish? It is either x or any of y and z. It could be like, if this is the x direction, we can clearly define this as x, but whether it is vibrating in this plane or in this plane or anywhere in this, on this rather anywhere, I mean, first of all, y and z are degenerate. I mean, we cannot strictly define, okay, this is my y axis, this is my z axis, because according to the cylindrical symmetry of the system, it is totally degenerate. So, we can take any two axes perpendicular to the x direction and mutually perpendicular to each other, we can define them as the y and z. Anyway, so let us say, for now, let us consider that the plane, it is oscillating in this plane and this axis is my z axis. So, the instantaneous position is given by z1 and z2. Okay. Also, for, I mean, right now we are not considering the motion, I mean, don't think that we are not considering the motion of this one. This one is also moving. So, when these two are coming down, please remember that we have to keep this, so for a normal mode vibration or a normal mode small oscillation, the center of mass should stay in the same place. So, if these two are coming down, this one has to go up. Similarly, if these two are going up, this one has to coming down, this one has to come down. So, let us assume that it has also a z movement in terms of given by the coordinate z1. So, we z2. So, we have the kinetic energy matrix T can be written as half m z1 dot square plus z3 dot square plus half capital M z2 dot square. So, this is the kinetic energy matrix. Now, our challenge is to convert this potential energy, which is written in terms of theta 1 and theta 2, we have to convert it in terms of z1, z2 and z3. Now, it turns out there is a way, clever way, we can simply write, because it is a small oscillation, we can simply write k s square and replace theta 1 and theta 2 by tan theta 1 plus tan theta 2. This is valid only for small oscillation. We could have taken sine also, but why tan? There is a reason. See, because it is a small oscillation. So, let us say this was the equilibrium position and this bond length A. So, this is my equilibrium bond length A, and sorry, not this, but let us say in this case this is my equilibrium bond length A. And because it is a small oscillation, we are not considering any stretching of the bond length. Okay. So, tan theta 1 will be z1 by A and tan theta 2 will be z3 by A, right or wrong? Wrong, because we have also need to consider the relative position of the middle molecule. Okay. So, it will not be z3 z1, but it will be z2 minus z1 minus z2 by A. I mean, it could be minus z, I mean the sign does not matter really here. And no, actually it does, because it will be z2 minus z1, right, and it will be z2 minus z3 by A. So, if this is z2, this is z1, so the gap between these two are simply z2 minus z1. Okay. Now, this is a way of transferring this thetas into z's. So, we go on and we write z2 minus z1 by A, or actually what happens is A cancels out nicely. So, it will simply be z2 minus z1 minus z2 plus z2 minus z3. So, it will be 2 z2 minus z3 whole square. Okay. Right. So, if we do that, if we open this up, so it will be 4 z2 square plus z1 square plus z3 square minus it will be, okay, let us see, it is very easy to make mistakes. Actually, it was better that way, because this way we are more prone to make mistakes. So, it will be z1 minus z2, or sorry, z2 minus z1 whole square, or plus z2 minus z3 whole square. Okay. So, if I now open up the brackets, it will be z2 minus z1 whole square plus z2 minus z3 whole square plus 2 z2 minus z1 Z2 minus Z3. Very good. Equal to half k Z1 square plus Z2 square minus 2 Z1 Z2 plus Z2 square plus Z3 square minus 2 Z2 Z3 minus 2 Z2 square, okay, minus 2 Z2 square Z2 square minus 2, okay, minus 2 Z1 Z2 Z1 Z2 minus 2 Z2 Z3 plus 2 Z1 Z3. Okay. So, it is a long term, and if I write it here, so V will be equal to half k Z1 square plus, okay. So, we have no, so it will be a plus Z2 square, sorry. So, it will be a Z2 square plus Z2 square plus Z2 square. So, it will be 4 Z2 square plus Z3 square, acha, 2 Z2 Z3 2 Z2 Z3 minus 4 Z2 Z3. So, Z2 Z3 is taken care of, and minus 2 Z1 Z2 minus 2 Z1 Z2 minus 4 Z1 Z2, right, and what is left is 2 Z1 Z3 plus 2 Z1 Z3. Okay. So, we have this expression for V, it is a long expression, but now if we construct the kinetic energy and potential energy matrices, please excuse me if I have made any mistake, because it is a very long algebraic calculation, difficult for me to see, it is very difficult. When I do it on pen and paper, it is easier. Okay. So, A is simply, okay, so we will get rid of the half first. A will be m capital M small m 0 and 0, or B is a long expression. Okay, so it will be 1 4 1 in the diagonal. Off diagonal we have Z2 Z3 and Z1 Z2, both are with a weight 4. So, we have to break it into 2 Z2 Z3 plus 2 Z3 Z2. Similarly, this will be 2 Z1 Z2 plus 2 Z2 Z1, so but minus 2 actually. So, it will be minus 2 here, minus 2 here. Similarly, Z2 Z3 also has this, and this will be 1 minus 1. So, it will be minus 1 minus 2 minus 2. Okay. So, job is half done. We can write this matrices A and B. That means we have almost finished our hard work. Next is we have to calculate the eigenvalues. So, once again B minus A B square equal to 0 determinant. So, if we do this, it will be 1 minus, sorry, there will be a k here. Okay. So, it will be k minus m p square. -2, -1, -2, 4 minus mp square, -2, -1, -2, 1 equal to 0. Oh, sorry, it will be k minus mp square, and we will have k everywhere. Okay. So, that is a long calculation once again. Now, we are running out of time a bit. So, what I will do is I will give you the final answer. So, I think you can do is you can follow this, you can open up this determinant and find out 3 distinct roots. Now, it will so happen that we have P1 equal to P2 equal to 0 and P3 will be equal to 2k by m 1 plus 2m by m. Right. Now, if you compare it with the frequencies we have got in case of just give me a second, where did I get it, where is it, right. So, if you compare it with the stretching mode frequencies, we have P1 equal to 0, P2 equal to root k by m and P3 equal to root over k by m 1 plus 2m by m. So, okay. This is say it is not about absolute comparison of the frequency, it is about this factor, and this factor, if you remember, was responsible for the fact that the center of mass is not moving. So, this is for the asymmetric stretching, when for this particular mode of oscillation, when this one is going this way, this one is, so we are talking stretching now, not bending. For this particular mode of vibration in stretching, so we have this for bending and this for stretching, right. So, for stretching, when these two were going in the same direction, this one was going in the opposite direction with a different weight in frequency, right. Now, this was responsible for the fact that even when all 3 masses are displacing, this center of mass remains at this position. Similarly, the same weight factor appears here, and by symmetry of the problem we can always find out exactly what is the what are the relative positions of center of mass, but without surprise you will find that for this frequency of oscillation, frequency of bending, the center of mass remains at the center. Okay. Now, there are 2 zero frequencies and these 2 corresponds to translations around any of the 2 axes. So, it is a, please remember that there is no x involved. So, these are all z. So, translation in z, and as I said, z and y, they are exactly they are degenerate axes, because we cannot really define a z and a y precisely. So, it remains, it gives you 2 perpendicular displacements, either along z or along y, mutually perpendicular directions. So, there is no bending, only this one corresponds to a bending, and of course, the bending will take place if you calculate the eigen frequency or eigen amplitudes, or rather amplitude vectors from this matrix. You will find out they are also scaled such that if these 2 are going up, this one is going down in a manner to keep the center of mass exactly on the same line. Okay. So, there is only one. So, we have seen that there are 2 stretching modes like symmetric stretching and antisymmetric stretching, but there is only one true bending mode, which is an antisymmetric bending. Okay. So, or rather not antisymmetric, asymmetric. Okay, so we are not. I am stopping here because we don't have enough time to show you the calculation, but only remaining calculation was to calculate the eigen amplitude matrix for this particular frequency, which I am pretty sure you can do it by yourself, and you will get no surprising answer to it. Okay, so that is the official end of this class. It has been a wonderful journey with all of you, and I hope you are also satisfied with the way we have handled our discussion forum, the way you have got your assignments. Assignments have not been very easy all the time, but frankly we could not have done better, because, and I feel that at some point we have to start attempting little difficult questions. That is important, otherwise we won't learn. Anyway, and also I need to mention the tremendous support I have got from Mr. Shubhabrato Ghosh, the TA of this particular course. He has been instrumental in preparing all the assignments and exam problem sets, the exam problems which we will be having very soon. And also he has helped me a lot in terms of fundamental understanding. Also I need to mention another of my colleagues' name, that is Professor Somudra Roy. He is also offering, in the same time he is offering his course was also running, that was on mathematical methods. He was the first one who introduced me to this excellent book by Professor Amal Kumar Raychaudhuri. Whenever I have difficulties in understanding any of the mathematical expression, any of the matrix equations, I always consulted him, and I always came up with a very distinct answer. Anyway, so I think it's time that we call it a day. Please keep writing me if you have any further questions in terms of classical mechanics, and I will be happy to answer that. Thank you all, and goodbye.